Okay. Right. So today we'll be doing a reductions part. So yeah, so this is like one of the most important tutorials because as you can imagine, one of the most important questions in your final exam would be to prove that a certain problem is NP-Completeness. Right there. Yeah. Okay. Okay, so let's start. So again, right? So a reminder from like last let me just get there. So a reminder from the last class. So what does it mean for a problem A to reduce to problem B? Okay. Okay, so what does that mean? Okay, suppose I have an instance of problem A that I don't know how to solve, but I know that how to solve any instance of problem B, right? So even though I cannot solve problem A on its own, what I can do is that I can convert the instance of problem A to an equivalent instance of problem B and then solve it in B's world. So solve it in B's world and bring the solution back to A's world, right? Okay, so that's essentially what reducing problem A to B means, right? Okay, so for decision problems, we know we give this reduction a certain name. We call this a carp reduction. So it's denoted like this. So A carp reduces to B. Okay, this B means efficiently means polynomial time. Okay, so A carp reduces to B. Okay, so now today we'll be talking about computation complexity theory, right? Okay, so before we actually begin talking about computation complexity theory, we need to understand the difference between certain terminologies, right? Okay, so we need to understand the difference between a certificate and instance of a problem. And what does it mean to verify a certificate? Okay, so it's easily understood if you actually take an example. So for example, suppose I give you a problem. So given a graph and two nodes, I ask, is there a path of cost at most k between them? So that's my question. Okay, so this is my problem. So a problem. So a problem is this problem is given a graph and two nodes. Is there a path of cost at most k? Okay. So what is an instance of a problem? Okay, so instance means, okay, you can think about instantiation of a problem. So one specific instance of a problem. Okay, okay. So an instance of a problem is basically one specific instantiation of a problem. Okay, okay. So for example, what is the input to the problem? Okay, so what are the inputs? For example, in this case, for this problem, the input would be a graph, 2 points, let's say 1 and 6, for example, and a budget. Okay. So this problem is given a graph and two nodes. Is there a path of cost at most k? The instance would be a specific instantiation of problem. So we can think about this informally as the input to the problem. So one thing, so the three inputs to this problem are a graph, we need 2 points and a budget. Okay, right. Yeah, so that's it is straightforward. But now we need to talk about what is certificate. Okay, so what is certificate? A certificate is something that claims to be the solution to the problem. Okay, so for example, we have this is a problem, right? And this is instead of a problem. Okay, now a certificate to this problem instance, so a certificate for this instance is something that claims to be the solution to the problem. Okay, so in this case, what is the solution to this problem? So what does the solution to this problem look like? Okay, so we need what? A path of cost at most k. Okay, so solution, a correct solution would be a path of cost at most k. So for example, suppose suppose that the 2 points are 0.6 and 0.4. So points 4 and 0.6. So we need to find a path from 0.4 to 0.6 whose budget is at most, whose cost is at most the budget is 10. So for example, the following certificate. For example, we can go like this, right? So 4, 3, 5, 6. The cost would be what? 2 plus 3 is 5, 5 plus 2. Okay, sorry. 2 plus 3 is 5, 5 plus 4 is 9. Okay, so this path would cost 9 and our budget is 10. Okay, so this is what we call a yes certificate. That means this is a certificate that proves that the problem is a yes instance. Okay, so now I'll ask you another question. Is this a certificate as well? How about this one? Is this a certificate as well? So recall that our problem is we have a graph, we have 2 points, for example, 0.1, 0.6, right? And a budget. So we need to find a path from 4 to 6 whose cost is at most a budget. So we know that this is a certificate, whatever. How about this one? Is this a certificate as well? Keep that. KJ, right? Yeah. So easy certificate.
Sorry, can you repeat again?
Oh, so you came now, right? Okay, so let's ask someone else. I just came. Ryan? Ryan, right? Okay. Okay, so anyone can answer? Can anyone answer? Is this a certificate? Okay, yeah, this is correct. This is certificate. But does this prove that the problem is yes instance?
No.
No. Correct, yeah. So that's the correct definition, right? So indeed, this is certificate because what is the definition of certificate? It's something that claims to be the solution to the problem. So it can be that it proves that the solution is yes instance or not. It's not yes instance. So it can claim that the problem is a yes instance or no instance. But in this case, this fails to prove that the problem is a yes instance because if you add the edges, add the edgeways along the path, it will exit 10. Okay, so indeed this is certificate yes, but it doesn't prove that the solution that it doesn't prove that the problem is a yes instance. In this case, how about this one? This is also a certificate yes, but this actually proves that the problem is a yes instance. This is also certificate yes, but it does not prove that the problem is a yes instance. The instance, yeah. Okay. Yeah, so you need to understand the distinction. Okay. Right. So now we know what's the difference between certificate, instance of a problem, and what does it mean to verify. Oh, okay, we need to talk about verifying certificate, but okay, so to verify a certificate, okay, so to verify a certificate in this example, you need to sum up the weights on the edges of the path given to you, right, by the certificate and check if its total cost is at most k. So verifying a certificate means essentially checking whether the certificate proves that the instance is a yes instance. Essentially, that's all that verification is. Okay. Now, what does it mean to efficiently verify? So one thing is to verify, the other thing is to efficiently verify. So to efficiently verify a certificate, this means to verify the certificate in time polynomial to the length of the input encoding. Okay. So to efficiently verify certificate means to verify certificate in time polynomial to the size of the input instance. Okay. I'm talking about the size of the input instance as the length of the input encoding. For example, we talked about what? Binary encoding is last, right? Okay. So if you want to verify a certificate efficiently, that means you must verify in time polynomial to the length of the input encoding. Okay. That's what is that is what is meant by verifying a certificate. Okay. So now the certificate, for example, a Sudoku grid, right? So problem would be does this Sudoku grid have a valid solution? So a proposed solution of weakness means certificate, right? A certificate would be a complete Sudoku grid. Okay. And verification means you check whether this proposed solution or the proposed certificate solves the problem. Okay, so whether it proves that this Sudoku instance is a yes solution, yes problem or not. Okay. And okay, so that's polynomial verification means you must verify this certificate in time polynomial to the length of the input encoding. Okay, so and so now we need to also talk about the class of problems. Okay. Okay, so P1. So what is the meaning of P? So P is what you have been dealing with all the time. The set of problems that can be solved in polynomial time. Okay, so essentially that's what P is, right? NP means the set of problems that have efficient verifiers for the certificate. So P means can be solved in polynomial time. NP means can be verified in polynomial time. That's the difference between P and NP. Okay. Okay, so clearly P is subset of NP because okay, so take any problem in P. So if you want to prove that this problem is also an NP, that means we need to show that any instance can be checked whether it's a yes instance or no instance in polynomial time. Or in another way of saying this is whether these problems have efficient verifiers for the certificate. So if someone gives you a P problem, if you want to show that that's an NP, you just throw away the certificate and just solve the problem because you already know how to solve it polynomial time and check whether it's a yes instance of the problem or the no instance of the problem, or whether the instance is yes or no. And that's pretty much it. Okay, so that means P is a subset of NP. I mean, these are all lecture content, so I'm just quickly recapping, right? So what does it mean for the problem to be an NP to be NP hard? Okay, a problem is NP hard if all the problems in NP reduce to X. Okay, so all problems in NP reduce to X. So the next important distinction is that X can be inside NP or not. So even if a problem is NP hard, it does not mean that this problem is inside NP. Okay, so it doesn't mean that it has to be inside NP. This problem can very well be outside NP, right? Okay, so yeah. So crucially, X can be inside NP or outside NP. We just don't know it, right? But what we do know is that all problems in NP reduces to this problem X. Okay. Yeah. And practically, because we can't reduce every NP problem to X because it takes too long, right? Just reduce a non-NP hard problem to X. Okay. So you want to show that a problem is NP hard, so that means you need to reduce every problem in NP to X. But since you cannot do that, Okay, what you can do is you reduce a single problem in NP you reduce a single NP hard problem to X. Okay, and because every NP problem reduces that problem, and by transitivity you can show that every problem in NP also reduces to this single problem called X. Again, all lecture time, right? So I'm just recapping. So what does it mean to be incomplete? A problem is NP complete if it's NP and NP hard. Okay, so this is special. So previously I told that NP hard problem can either be in NP or it can be outside of NP. NP complete problems lie strictly within NP. That means they are NP hard and also lie in NP. Okay. Yeah, so essentially like something like this. Okay. It's in NP and it's NP hard. That means every problem in NP reduces to it. Okay. Okay, so let's start. Which of the following imply P equals to NP? Okay, so currently we know that P is subset of NP. If we know that there's a problem in P that is also NP complete, does that imply that P equals NP? I.e., does it imply that NP is a subset of P? This is a little bit non-trivial, but it's okay. Yeah, Keisha.
Yeah, correct.
Yeah, what?
Because all the NP problems can be reduced to NP complete, and if let's say NP complete problem can be solved in polynomial plane also, this means like NP can be reduced to NP complete, and then NP complete is equal P, and then it's seriously means that P is equal to NP.
Okay, yeah, that's a great idea. But okay, so let's go slowly, right? So if there's a problem in P that is NP complete, okay. So what does it mean to be NP complete? That means it is NP hard and NP, right? So in particular, it is NP hard. So if this problem, which is in P, is also NP hard, then what's the definition of NP hard? That means every problem in NP reduces to that problem, right? But we know that same problem is NP as well, right? So that means it can be solved in polynomial time. That means what? Every problem in every problem in NP reduces to this NP hard problem, which can also be solved in polynomial time. Okay. So therefore, so what does this mean? So that means what? If every problem in NP reduces this single problem that can be solved in polynomial time, then that means every problem in NP can be solved in polynomial time. Therefore, if you take any problem in NP, that also belongs to P. So we also can show that NP is a subset of P. So combining these two, we can get that P equals NP. Okay, which is wonderful if it happens, but clearly no one believes that it is true. Okay, so P is I mean the most logical thing is to believe that P equals not NP. Okay, okay. Yeah, so if there's a problem in P that's also NP complete, then surely it will prove that P equals NP. Okay, next one. If there's a problem in P that's also in NP. Yeah, right. Does this prove that P equals NP? If you can show that there's a problem in P that's also NP.
My brain is off.
You want to give it someone else or?
Sure.
Oh wait. I mean only you do.
I'll get there eventually.
So you want me to continue?
Yeah, just continue.
Okay. Okay, so if there's a problem in P that's also NP, does it prove that P equals NP? Okay. Okay. So we know that P equals NP. P equals a subset of NP, right? P is a subset of NP, right? So does this show that NP is a subset of P? No, right? So what we're saying is that there is a problem in P that's also NP. So that means we're saying that there is a problem in P that's also belongs in NP. I mean, we know that, right? Okay, I mean, here there's a problem in P that's also in NP. Right? So that doesn't say anything about NP being a subset of P, right? It's okay. I mean, clear that doesn't help you. That's false. That this doesn't say anything. I mean, we already know that, right? See, there's a problem in NP that's also NP hard. Does this show that that P equals to NP? You want to try?
You do that. Because P is a subset of NP, so the problem NP that NP hard will not NP.
Yeah, okay. I mean, yeah, you're trying to connect it to this one, right? Oh, well, okay, fine. So, okay, I want to tell you. Well, I want you to tell me what does this statement say? There is a problem in NP that's also NP. What is it saying? Okay, first of all, I want you to tell me whether this statement is true or false. Okay. Is this statement true or false? Like anyone can answer. Is there a problem in NP that's also NP hard? Yeah. So this is the definition of NP complete, right? Okay. So false, right? This false in the sense this will not show that this P equals NP. Okay, this by itself is a true statement, right? I mean, obvious, right? Okay, but this will not prove that P equals NP because what this is saying is that there is some NP complete problem. That's all. Okay. I mean, we are just saying that there is a problem in NP. That's all that we have. I mean, that means this problem is NP complete. Okay. I mean, so this false. This doesn't prove that P equals NP. Okay? It's saying nothing because we already know that. Okay. Now let's come to the important question. Question number 2. So given a subset, given a multiset Sn, okay, let me just zoom in. Okay. Given a multiset S of n, non-negative integers, okay, S1 through Sn, and an integer W, the subset problem asks: does there exist a subset I of indices, okay, so 1 through n, such that these integers sum up to W? Okay, so we have a multiset S1 through Sn, okay, and a target W. Is there a subset of integers from this subset such that they add up to W? That's essentially. Okay, so for example, given n equals 5 and s equals to this many, and a target of 7, then it is the yes instance with a certificate that proves that it's the yes instance as, for example, if you choose the indices 0, 1, 3, identical to choosing the values 5, 1, 1, then they sum to 7. Therefore, this is a yes instance of the problem. Okay. Subset sum is very, I mean, you're very familiar with it, right? Okay, so we want to show that subset sum is NP complete. So to prove that it is NP complete, we need to show, yeah, let's ask Ryan. To show that the problem is NP complete, we need to show two things, right? Okay. I'm trying to give you the chance to get full marks.
I'm trying to.
Okay, so to prove that the problem is NP complete, we need to show that it is NP and also NP hard, right? Okay, so to prove that it is NP is very easy. Okay, so what should you do? You must just prove that any certificate can be verified in polynomial time with respect to the length of the input encoding, right? So that's NP. So for example, given a certificate I, okay, that claims to be the solution to some instance of subset sum, right? Okay, let me zoom out. Okay, so given a certificate I that claims to be the solution to some instance of subset sum, how to verify it efficiently? That means how to verify whether this certificate proves that this instance is a yes instance. Okay, how to? Okay, essentially I'm asking, does this certificate solve the problem? Not very naively, that's what I'm asking. So how can you check? Okay, let's ask that from Ryan. That should be very easy.
If you certificate or the set of values, just iterate through the values and then you sum.
Okay. Okay, correct. Yeah, so simply just add up the values and see whether it's equal to W. So it takes time for it, right? And previously I told, right? Because we assume that each integer fits into a 32 or 64-bit number, right? So therefore, each integer takes like a constant number of bits to encode. So we have n integers, therefore n times, I mean, if you consider W as well, you have like n plus 1 times 32 bits, right? So therefore, length of the input encoding is also theta n. And the time taken is also On, so therefore it's polynomial in the length of the encoding size. So crucially, you only need to ensure that the verifier runs in time polynomial to the size of the encoding. Okay, that's essentially what you need to do. You don't need to find a verifier that's like crazy fast. Essentially, it does not have to be the fastest possible verifier. You just need to ensure that your verifier runs in time polynomial in the length of the input encoding. Okay, so in the exam, please don't leave this question blank because why? This question is 3 marks. Okay, so essentially, I mean, if you notice, this question is 3 marks. Okay, you only need to verify that a certificate can be verified in time polynomial to the length of the encoding. That's the most easiest question I'm pretty sure you have encountered in your 3 or 4 years in CS. Okay, like literally, please don't keep this question blank. Okay, because the crucial thing is it does not have to be the fastest possible. The only thing that it must satisfy that it can be solved in time. I mean, it can be verified in time polynomial in the length of the input encoding. That's it. Okay. Yeah. Okay. So now let's show that this is a hard one. Okay. So this is the easy one. So this is the hard one. Okay, in the exam. Okay, so to prove that the problem is NP hard, that's the hard one. This is the easy one. Okay. Okay. So let's prove that subsystem is NP hard by showing that 3-set reduces subsystem. So in the exam, usually they will give you the problem to reduce from. Okay. Usually, because the professors will not want like everyone reducing from like a 10,000 different NP hard problems, then yeah, they'll have a heart attack trying to like grade the scripts, right? So they usually give you the problem to reduce from. Even if they do give, still it will be a little bit challenging. Okay, but still, but in recent times the question has been very easy. If you check our paper, I guess this is quite straightforward actually. Okay, that means our one was like 2024 sem 1. Yeah, 24-25 sem 1. Okay, so let's prove the subsystem is NP hard by showing that 3-set reduces subsystem. Okay, so now listen very carefully, right? So what's our goal? So our goal is what? So we have a problem called 3-set. Now we want to reduce it to a problem called subsystem. Okay. So we don't know how to solve. Okay. So we don't know how to solve 3-set, but we know how to solve a problem called subsystem. So that means we are trying to solve 3-set using subsystem. Okay. So essentially that's pretty much it. Okay. Okay. So what's our goal? We want to find a transformation from instances alpha of 3-set to instances beta of subsystem such that if alpha is yes, then this implies that beta is yes. And if beta is yes, this implies that alpha is yes. So yes implies yes and yes implies yes, both ways, right? Okay, because we want to solve subsets, we want to solve 3-set using subsystem. Okay, so if you cannot show that like yes of subsystem implies yes of 3-set, if you cannot show it even to one direction, then that means your transformation is wrong. Okay, because you cannot solve it using subsystem. Okay. So crucial, you want to find the transformation from instance alpha of 3-set to instance beta of subsystem such that alpha is yes implies that beta is yes and beta is yes implies alpha is yes. Okay. Yeah, so let's begin. So now let's consider a 3-set formula. Okay, so in this formula we have what? N variables, x1 through xn, and we have m clauses. So n variables and m clauses. Okay. So n for number of variables, m for the number of clauses. So we need to define an input. Okay, so we want to define a sensible input to subset sum, which allows you to solve 3-set using subset sum. Okay, so we want to define an input to the subset sum problem somehow. Okay, so we want to define an equivalent input. Usually, the technical word is we want to define equivalent input. Okay, so because we want to solve 3-set using subset sum, so you better ensure that your input to the subset sum problem is kind of equivalent to 3-set problem. Otherwise, you're not solving the same thing. Okay, so to reduce the problem, with 3-set to subsystem, we need to specify the inputs to your what subsystem problem. Okay, so in this case, what are the inputs to subsystem problem? So we need to define the numbers wi. Okay, why wi? First, we need to define the way your multi-set, right, to your subsystem problem, right? So we want to define the numbers wi and a target sum w that is equivalent to 3-set problem. Okay, so we want to define the input to the subsystem problem, which are the numbers wi and the target sum w that is equivalent to this 3-set problem. Okay, so let's begin. So again, recall what is xi before moving on. So what is xi again? Yeah, so anyone can answer because like the last person is not here. Keep done. Yeah, so what is xi here? Yeah, quickly.
The variable.
Yeah, the variables, right? So one of these variables, right? So one of these variables is xi. So I just want to ask just to keep you on track. Okay, so for each xi, we start by defining two numbers for it. Okay, so we have two numbers ai and bi for each xi. Okay, why do I define two numbers? Because if I include ai, this means I would set xi to true, and if I include bi, this means setting xi to false. Okay, so for each variable, I define two numbers ai and bi. So if I include ai, that means I set xi to true, and if I include bi, that means I set xi to false. So there is 1-to-1 correspondence between true, false, and ai, bi for each variable. Okay, so I'm trying to get this equivalence, right? Okay. Okay, so recall where do ai and bi live? In the which problem? In which problem does ai and bi live? in the subsystem problem. Okay, now we're going to define what AI and BI are. So what is the form of AI and BI? Okay, so here's what it's going to look like. So for all variables 1 through n, we'll define AI and BI. So AI looks like this. So AI equals to 10 to the m plus I plus summation of 10 to the j for all j such that Cj contains xi. Okay, all right. So what's m here? Yeah. So m is the number of clauses. Okay. N is the number of variables. Okay. So for each variable, right? For each variable, okay, 1 through n. I mean, each variable x1 through xn, we define AI and BI. AI is of the form 10 to the n plus I plus this summand over here. Okay. Okay. So so let's slowly look at this in a bit. Okay. Now I'll define BI as well. Essentially the same thing as AI, but okay, so BI equals 10 to the n plus I plus summation of 10 to the j such that j loops over clauses, I mean Cj, such that it contains xi bar. So previously we loop over clauses that contains xi. Now we loop over all clauses that contain xi bar. Okay. Okay. So now let's look at an example to understand like what these numbers are doing. Okay. For example, if the 3-set instance was like this, so suppose I give you a 3-set instance like this. Okay. So what? So we have x1 or x2 bar or x3 and x1 or x2 or x3 bar. So if I give you this instance, now for each of these variables, how many? So what are the variables present? That is x1, x2, and x3, right? So for each of those variables, I need to define what? AIs and BIs, right? Okay. So now let's see what these AIs and BIs actually look like. Okay. Now here look like. So consider x1. So I need to define two variables, two numbers, a1 and b1. Okay, so what is a1? 10 to the, okay, what's the number of clauses here? 2. So 10 to the 2 plus 1. Why this 1 comes here? Because I equals to 1 here. Okay, I equals to, in this case, I equals to 1 here. Okay, a1 is equal to 10 to the 2 plus 1 plus, now I need to loop over every j such that clause Cj contains x1. Now imagine that this is so my drawing tablet broke down, so very unfortunate. So I just put this one as clause number 1, and I call this clause number 2. Yeah, okay. Okay, so I'll call this clause number 1, I call this clause number 2. Okay, so now I'm going to go over every j such that clause Cj contains x1. So out of these clauses, which clause contains x1? Yeah, 1 and 2, right? So I add 10 to the 1 plus 10 to the 2. Okay, because those are the j's that, so those are the j's such that Cj contains x1. So those j's are 1 and 2 because C1 and C2 contain x1. Okay. Now let's consider how to define B1 for, define B1 for x1. So B1 is equal to 10 to the m plus 1, m plus 2. Oh, sorry, I'm talking about Bi equals 10 to the m plus I. So therefore I is equal to 1 and m is equal to 2. So therefore B1 is equals to 10 to the 2 plus 1 because m is 2 plus, now we're going to look at all the clauses Cj such that Cj contains x1 bar. So which clauses contain x1 bar? None. So therefore we are 0. Okay. Now let's look at x2. Okay, so we are going to define a2 and b2. So for a2, we are going to what? So we are going to go over. Okay, first of all, a2 is equal to 10 to the 2 plus 2. Okay, so m is 2 and I is also 2. A2 is equal to 10 to the 2 plus 2 plus we are going to go over all all j's such that clause Cj contains x2. Okay, now look here. Out of these two clauses, which contains x2? Okay, yeah, 2 contains. How about clause number 1? Does it contain x2? No, it contains x2 bar. Okay, so that's the distinction. Okay, so for a2, we define what? A2 equals 10 to the 2 plus 2 plus the only clause that contains x2 as a literal is the second clause. Therefore, we add 10 to the 2. And similarly, for B2, we add 10 to the 2 plus 2. Okay, 10 to the 2 plus 2 because 2 m is 2 and also I equals 2. Plus, we go over all j such that Cj contains x2 bar. So the only clause that contains x2 bar is the first clause. So we add 10 to the 1. And similarly for x3 you define. Okay, so x3 a3 equals 10 to the 2 plus 3 plus you look at every clause that contains a3. X3. In this case, only a first clause contains x3, so you add 10 to the 1. Okay. For B3, you go every clause that contains x3 bar, which is only the second clause, and you add 10 to the 2. So very easy. Is that okay so far? Okay. Sorry, yeah. Okay, so now we are going to define the transformation, right? So like I did for the Hamiltonian cycle and traveling salesman problem, I'm going to always look at what a S instance of 3 set is and the corresponding subset of numbers so far containing AI if xi equals 2 and containing bi if xi equals false. So previously what did I do? I defined what? Yes, I looked at an instance of the S instance of traveling salesman problem. I want to define a transformation such as S instance of traveling salesman implies S instance of Hamiltonian cycle. So in this case, I also use the same kind of intuition. I look at S instance of 3 set. Now I look at what the corresponding subset of numbers so far containing AI if xi equals 2 and contain bi if xi equals false is. Okay. So the main claim that I'm going to make is that the resulting sum is of the form as follows. Okay. So now I define, recall, right? I define for each xi, I define ai and bi. Okay. So for a S instance of 3 set, now you consider the corresponding subset of numbers so far that I choose. For example, if I set xi equals true, I choose ai, and if xi equals false, I choose bi. Now consider those numbers, right? So the first claim is that it has a 1 in the leading n digits. Okay, so why is that? Because this corresponds to 10 to the n plus I for I equals 1 through n. That means, because why? For each xi, okay, so for each xi, you have to set either true or false, right? So if you set true, you choose a1, xi. If you set xi equals false, you choose bi. Okay. So out of ai or bi, exactly one of them is chosen. Exactly one of them is chosen, right? Right? Okay. So currently the sum will look like this, right? So you have n ones and you have the rest of the number. Because if you, I'm saying consider S instance of 3 set. Now you consider the corresponding subset of numbers so far containing ai if xi equals 2 and containing bi if xi equals false. So if you add up all those numbers, right, it must have a 1 in the leading n regions. Because for xi, you either include ai or bi, right? Okay. And I defined ai and bi in such a way, right? Because this leading 10 to the n plus I, okay, is if you consider the number called, let's say 10 to the n plus 3, okay, if you consider number 10 to the n plus 3, for example, if I is 3, 10 to the n plus 3 is 1 only in A3 and B3. None of the other numbers have a 1 in the 10 to the n plus 3 digits, that digit in the numbers. Okay. So only A3 and B3 have a 1 in the position of 10 to the n plus 3. Because no other number has a 1 there. Okay. Is that okay? Okay, so this should be very easy, but it will take some time to understand, but it's nothing hard. Okay. Okay. Yeah. Okay. Yeah. So it has a 1 in the leading n digits. Okay, corresponding to 10 to the n plus I for I was 1 through n. As we include either ai or bi. Because if you said xi, you choose if you said xi true, you choose ai. If you said xi false, you choose bi. Therefore, since you include either ai or bi, therefore the leading n digits will be n1 strictly. Okay. And we don't know what the rest of the number is for now. But for sure, the first n digit will be 1. Okay, is that clear? Yeah, any questions? So you understood, is it? If Valentin, you have a question?
Yeah, some that you see some will do like that.
Yeah.
But like, and then maybe you explain this later, but let's say I said it's only true and then exponentially. What if I add up all the numbers that give that I have here the numbers when they overflow.
Okay, and I come to that point. It won't overflow. I'll show you why. Okay, that's a very good observation. Now it won't overflow. Yeah, I'll come to that in a bit. Okay. For now, the first n digits is exactly 1. Okay. And it has a 1, 2, or 3 in the next m digits. That means for the next m digits, it has 1, 2, or 3. Why is that the case? Because the digit of 10 to the j, where j is at most m, is exactly the number of true letters in clause j. Okay, because the 10, so yeah, because the digit of 10 to the j in the sum is exactly the number of letters in clause, true letters in clause j. Okay, for example, now look here, right? So, for example, if you look at the sum of all those numbers ai's and bi's that we choose, right? For example, if x1 is true, you choose a1. If x2 is false, you choose b2, and so on, right? Now you look at the j, look at this j bit here, right? This j bit corresponds to the jth clause, right? Okay, suppose that the jth clause looks like this. That means x7 or x9 bar or x4 bar. Suppose it looks like this. Now, the only numbers that contain a 1 in that jth position is x7, sorry, a7, b9, and b4. Only these numbers have a 1 in the jth position. Now, why does a7 have 1 in the position? Because okay, so when we defined a7, it was defined for x7, right? So, because we see that x7 is present in the jth clause, therefore we have that a7 will contain 1 in this jth position, right? Okay. Is that okay? Right? b9 will also contain 1 in that position because we know that x9 bar is in this jth clause. Therefore what? b9 will contain 1 in the jth position. Okay, and also b4 will contain 1 in that position because x4 bar is in this clause. Okay. Now I'm going to ask a question. Why doesn't b7 have 1 in the position? Why doesn't b7 have 1 in the position? So for b7 to have 1 in the position, therefore we need to ensure that what x7 bar is in this clause. So is x7 bar in this clause? No, right? Therefore what? b7 will not have 1 in the jth position. That means in this position, b7, right, will never have a 1 in the, will never have a 1 in that place because x7 bar is not in this clause. Now, because 3 sat is satisfied, at least one literal out of these 3 must be true, right? Okay. Okay. So either x7 is true, or x9 bar is true, or x4 bar is true. So if x7 is true, that means we need to include a7, right? If x9 bar is true, then that means x9 is false. That means we include b9, right? If x4 bar is true, that means x4 is false. That means we need to include b4. So that means we need to include like at least one of these, right? So by including at least one of these 3 numbers, right, and at most 3, because there are only you can only include at most 3 of these numbers, right, from whatever you define. That means out of a7, b7, b9, a9, and a4 and b4, we can only include at most 3 of these numbers, right? Precisely out of only these 3 numbers, because only these 3 numbers have 1 in the jth position, right? So out of these 3 numbers, you can include at most 3. Okay. So by including at least one of these numbers and at most 3 of these numbers, we guarantee that the jth bit is at least 1 and at most 3. Okay, so why should we include at least one of these numbers? Because why? In the jth clause, at least one of the letters must be true. Therefore, by this logic, at least one of these numbers must be included. Therefore, jth bit, where j is at most m, must be at least 1. It also must be at most 3 because the only numbers that contain a 1 in the jth position are only these 3 numbers. Nice. Right. Okay. Yeah. So, and that jth digit of the sum must be non-zero if the assignment satisfies the three-step formula. Because at least one of these numbers must be included, and at most 3 of these numbers must be included because you can only include only these 3 numbers to get a 1 in that position. Okay, only these 3 numbers have 1 in that position. So even if you include all 3, the sum, the digit of the jth position, right, this position will be at most 3, but will be at least 1. Okay. So now the sum will look like this. So we'll have n ones and m digits, and each of these m digits will be either 1, 2, or 3. Okay. Okay. So we have n ones and m digits, but the last m digits will be either 1, 2, or 3. Guaranteed. Okay. Right. So let's continue. And just one nitpick, right? And it also has a 0 in the last digit, like this. Why? Just it's a my technical detail, but it's okay. Yeah, why? Who can tell me? As in, I'm talking about this 0 here.
Start one, pick one.
Yeah. Essentially, because you add for because we are indices are from 1 onwards, right? So even if you add like these 10 to the j's, this j will be at least 1. Okay. Okay, so that means okay, did I make mistake? Yeah, okay, true, that's correct. Okay. Yeah, so because all these j's, our indices are from 1 to m, and indices are 1 to m, and variables are from 1 to n. Because and then if you consider 10 to the 1, 10 to the 2, 10 to the 3, all these numbers have 10 to the 0th position is always 0, and only 10 to the 1, 10 to the 2, 10 to the 3 position will be. Okay, therefore the last digit will be 0, guaranteed. Okay, yeah. Okay, now to turn this into an answer for the subsystem problem, we still need to add a few more numbers because we didn't even specify the target weight, right? So we specify the target weight as follows. The target weight is essentially like this. So we have n ones and 3 m's. So our target weight is n ones and 3 m's and a 1 0 at the end. These are target W for the subsystem problem. Okay. Okay. And in addition to defining AIs and PIs, we also define a few more numbers, CJs and DJs. Okay, so let's look at what these are. Okay. So we also need to add CJ and DJ equals to 10 to the J for J equals 1 through N. Okay. So these are, recall, these are for the clauses. Okay. These are the clauses, strictly for the clauses. For J equals 1 through M. So for every clause, 1 through M, we define two more numbers called CJ and DJ. Okay. For J equals 1 through M. So this is a small technicality to make the proof work. Okay. If you don't do this, your proof will break down, and you will realize that your proof breaks down, and then you come back and define CJ and DJ. Okay. That's the reason. Okay. So it won't be obvious to you that you should define this, but after you define your proof and you try to prove it, then you realize that it doesn't work. Then you come back and add these numbers. Okay. That's how it works. Okay. So our W looks like this. We have n ones and 3 m's and 1 0, and also add the following numbers to our set CJ and DJ for J equals 1 through M, 10 to J. So at the end, transformation is finally complete. So now the hard part is done. We need to ensure that yes instead of 3 implies yes instead of subsystem. Now this is actually very easy because we did the hard work already. Okay, now look here. So for any instance, for any yes instead of 3, right? We consider every variable xi. Now, if xi is true, we need to select ai in the subsystem. Okay, and if xi is false, we need to select bi in the subsystem. So that's how we did. That's how we solve this problem, right? So now, if you see that, okay, so by the claim above, right? By these claims above, right? So easy to see that this gets the leading first n digits of the W correctly. Because why? Because for each variable xi, we either include ai or bi. Okay. Because if xi is true, we select ai. If xi is false, we select bi. So if you add the numbers, if you add these numbers that you choose, then guaranteed the first n digits of your sum will be 1. So therefore, we get the first n digits of W correctly. Okay. Now listen very carefully. To make the remaining digits, okay. Now the next thing. Okay. So we already have this part correctly. Now look at these m digits that come after the first n ones, right? Now we know that if I add up all the AIs and BIs, right, I can get what 1, 2, or 3, 1, 2, or 3, 1, 2, or 3 for the next m digits, right? Right? Okay. But we need to make 3, 3, 3, 3, 3, right? Okay. But we define CJ and DJ for that very purpose. Okay, so we define CJ and DJ for J equals 1 through M for that very purpose. Because if it's 1, 2, or 3, okay. Okay, so if it's 3, you don't need to add this CJ here, right? If it's 2, then we need to add 1 CJ to get it to 3. If it's 1, for example, then you need to add both CJ and DJ for this J position to get it to 3. Okay, I mean essentially like that. Okay, so depending on what this number becomes after you add your AJs and BJs, AIs and BIs, okay, you may need to add either CJ or both CJ and DJ to get it to 3 here. Okay, because these numbers are either 1, 2, or 3 after you add up your AIs and BIs, but you need 3, 3, 3, 3, 3. So depending on whether it's 1, 2, 3, you may need to add only CJ, or both CJ and DJ, or even none. Okay, so if it's already 3, you don't need to add anything. If it's 2, you need to add CJ. If it's 1, you need to add both CJ and DJ. Okay. Okay. Yeah. Okay, so to make the remaining digits, we may need to add CJ or both CJ and DJ, or even none of them. Right? If it's already 3, you don't need to add anything. Depending if the digit of 10 to the J is either 3, 2, or 1 in the sum of AIs and BIs. Okay. And I mean, if you can do this, which you can do, if the subsum is if the three-side problem is yes, and therefore your subsum problem is also yes. Okay. So now we have to prove that if it's yes for subsum, it's also yes for three-side. It's also fairly straightforward, but you need to be a little bit more careful. Okay, now look here, right? Now know that for any digit 10 to the k, there must be at most 5 numbers with the 1 in that position. Why? Okay, for the first n digits, okay, how many numbers have 1 in the position? That means let's say I consider okay, so let's say I consider this position. How many numbers have 1 in that position? Out of the AIs and BIs and the CJs and DJs, how many numbers have 1 in that position? Only 2, right? Why? Only A1. Okay, sorry. Okay, not A1, but rather only A, N, and B, N have a 1 in the question, right? No other number has 1 in the question. Okay. Now consider one of these digits. Okay, if you consider single digit, at most how many numbers will have 1 in the question? Okay, that's a bit complicated, but I'll get to that slowly. Okay. Now, okay, yeah. So know that for any digit 10 to the k, there are at most 5 numbers with a 1 in that digit. Okay. Okay, if for j equals 1, at most m. Let's consider this part, right? They are the 3 literals corresponding to the clause k, right? The 3 literals correspond to the clause k, if k is at most m, and ck and dk. Okay, so let's give the story. And at most 2, 4, k strictly greater than. Okay, let's go through this slowly. So take the same example as this thing here, right? So if you consider clause j, that means corresponding to the j position, right? Only A7 has a 1 in that position, B9 has a 1 in that position, and also B4 has a 1 in that position. So we already did that here, right? And in addition to that, we know that what CJ and DJ also have 1 in the position, right? Okay, so at most, how many numbers have 1 in the position? We have 1, 2, 3, and CJ and DJ. Okay, so A7, B9, and B4 have 1 in that position, and also CJ and DJ also have 1 in the position. Okay, for this J3. So at most 5 numbers, right? Okay, right. Yeah, so with only 5 numbers in any position, adding whatever subset of numbers will never cause a carryover. Okay, okay, because if you have at most 5 ones in any position, so even if you add all the numbers, you will never get a carryover, right? Because to get a carryover, you need to get like you need to get 10, right? So if you get 10, it carries over to the next one. Okay. So with only 5 ones in any position, adding whatever subset of numbers will never cause a carryover. So we can only get the total W by including the right number of ones in any big position. Okay. So how does W look? You have n ones, 3 m's, and 0, right? So this means that we can never choose both A, I and Bi. Why? If you choose both A, I and Bi, now recall we're trying to prove yes of subset sum implies yes of three set. If you choose both A, I and Bi, then you violate this part, right? Right? If you never choose any of A, I and Bi, again it violates this part, right? Right? Because then it will be 0 for a certain position. That means we can, I mean, if these two are gone, then the only possibility is we can only choose either one of AI or BI. Right? Because there are four possibilities. Either you choose both, either you leave both, or choose either one of both, either one of AI or BI. So that directly corresponds to setting xi to true or false, right? Okay, so if we can only choose either one of AI or BI, that corresponds to setting either xi to be true or false. Okay, so if you choose AI, then just set xi to be true, and if you choose BI, then set xi to be false. Okay, right. So again, right? If you choose, if you consider any bit position j in the sum where j is at most m, okay, so that means we are looking at this part, right? So this bit corresponds to jth clause, right? My question is it possible that if a subset sum is a yes instance, right? Okay, so my question is it possible that if the subset sum is a yes instance, is it possible that none of the AIs or BIs that have a 1 in this position, in this jth position, were selected? That none of these were selected. That means I'm asking, for example, in the previous clause here, right? In this clause, jth clause that corresponds to the jth bit, is it possible that none of these three numbers are selected? A7, B9, or B4. Is it possible? Okay, so if if they were not selected, then what's the largest sum that you can get in that position? 2. Yeah, 2, right? So you cannot, right? Therefore, you need to choose at least one of those AIs or BIs that have a 1 in the position, right? Okay, but that corresponds to what? Setting at least one literal in that clause to be true, right? Okay, I mean, slowly you will get it, okay? This means that at least one of the AIs or BIs that have a 1 in that position must be included. That means clause J is satisfied. Okay, but J was arbitrary. That means every clause is satisfied. Therefore, 332 is also satisfied. Okay. I mean, this proof is a little bit complicated. Okay. So when I was solving, I got the right idea, but I also wasn't able to solve it. Okay, so don't worry if you didn't get it in the first view, right? Just take some time to slowly go through it, right? Yeah, I think this is the only question that I couldn't solve properly. I took a long time, but I couldn't solve it. But this automatically makes three such sense. So yes implies yes and yes implies yes. Okay. Okay, so question number 4 is in comparison. Okay, see, I have something to give you because like I always do something on the last day. But not many people came, so I don't know whether that will so you can take time faster. So in comparison, right? So the next question, which is like find family, it's like very trivial, okay? Because compared to like proving the right? Okay, but as you can see, I always run out of time when discussing the first question. So for the last like 2 semesters ITA, this module, right? I always run out of time for this question, right? But this question is very, very easy. Like this question is kind of representative of what you can get in the exam. Okay. Okay, so this question is kind of representative of what you can get in the exam. The previous one is a little bit more difficult, more challenging. Okay. This one is very easy. So please try to do this question right on your own, right? Because this one is representative of the type of difficulty that you will get in the exam. This question is like very easy. I hope. Okay, so I saw this question in like 15 minutes, but like this question is like very straightforward. Okay, it's nothing much compared to previous ones. But as you can see, I ran out of time again. So what I'll do is I'll record a video for this and I'll send it to you, right? But please try to solve it because this is very easy. Okay, and this kind of question that you will get in the exam. Okay. I mean, you can take 2 if you want. Okay, so that's pretty much it for my teaching. Yeah, this one is very easy. You don't need to think about it at all. You can try, but I'll record videos in here, right? Yeah. Okay, so let me quickly take attendance, right? Gary is here. Jeevan is here. Ethan is not here again. Greenfeng is not here. Rachel is here. Darren is here. Oh, really? Yuna is here. Nicholas? Nicholas was here, but he was. Christopher? Chao Shen? AJ Ryan? Nathan? Okay, so you should take a photo on the last day. So, okay, so you guys can come to the center. Okay, I'll come on. Okay.
What do you do with this?
Yeah, you guys can. Okay, yeah, you guys can sit in the front. Oh, maybe leave some space for me and just sit out here.
Yeah, I need to crouch. I'm a bit tall.
I mean, yeah, you guys can stand, but like
Everyone,
because otherwise you can't. You guys can.
I will sit for them.
And you can sit here.
I want to sit there. You want to go
I'll just be taking shots so you can change your pose. Roll and stretch.
so professional.
3, 2, 1. Y'all want a 0.5 or something?
Sure.
Oh, it is so sick.
Okay. Thanks so much.
Sorry.
You want?